Hey guys, welcome. This is for those who have missed, this is the Chapter 23 video. Thankfully, Chapter 23 is very close in spirit to what we did in Chapters 18 through 22. We're going to start off with a look back to things that were familiar, that you've seen, and then relate it to this new t-distribution that we have that will replace the normal bell curve for sample means given certain circumstances. And we'll move forward from there. We're going to hit all of Chapter 23 in this video. It may take us a little while. I don't think it'll be too bad. Let's see. Let's start now. All right, sampling distribution of X bar. This we talked about in Chapter 18. And this was actually the last time we talked about sample means through those 5 chapters. Okay, so the way that it worked is you could use a normal bell curve so long as you had given to you the population mean and the population standard deviation. So for instance, maybe the sample means that I'm taking that would fit on my bell curve, all these different sample means that we could observe. Maybe they are from samples of size 50 students from Yorktown High School, and we're just averaging out their heights. Okay? So you could use the normal bell curve so long as you knew the population mean, maybe of all 800-ish students within the high school, you knew for a fact that 5'6" was the average height. And maybe you knew that the standard deviation, again thinking about that as the average variation from the mean, maybe the standard deviation was like 3 inches, okay? So if you knew those things, you could use a normal bell curve and it would tell you how frequently you would get sample means in particular places. We will keep another X bar here. Okay, so the expected value of X bar, the expected value of one sample mean would just be the population mean, and the standard deviation of X bar from the central limit theorem is the standard deviation of your individual students divided through by the square root of your sample size, which, like we were talking about earlier, if we're taking samples of size 50 from the school, that would be the square root of 50. Okay? And then let's compare that to, real quick, the sampling distribution of p hat. Okay, so if we know p, the population proportion, maybe we want population proportion of people within the high school who drink milk. Okay? You can talk about samples of maybe size 50, will be consistent in our sample sizes here, and the sample proportions that you would see using, I'm not sure why I put a big caret symbol there. Well, okay, let's erase that. P hat, okay. All right, so you could talk about the normal bell curve describing for you sample proportions of students within the school who drink milk, okay? And the expected value of one sample proportion of maybe 50 students should just be the same as your population proportion of students who drink milk. And the standard deviation of p hat, this you've used many, many times. This is the PQ all over n within a radical, okay? Well, so that's great, and it's nice to know that the normal bell curve will work for sample means or for sample proportions, so long as you have the 2 population statistics or parameters, mu and sigma, the mean and the standard deviation for X bar, and if you know the population proportion for sample proportions, okay? Well, so the question is, what happens when you don't have those things? Because realistically, just think real world with me for a second. Is it more useful to, or would you more often have information about a whole group of people or things that are similar? Maybe everyone within the United States. Or is it more likely to have information about a sample of people within the United States? Well, clearly the sample is the more likely of the 2. So it's great that the normal bell curve works, but it's not practical. There are a lot of times when you don't have these given. You don't have the sample proportion given, okay? Well, let's say for a second that instead of mu and sigma, our givens are actually just X bar and S. Now, X bar, remember, is a sample mean, and S is a sample standard deviation. Well then, we would estimate that the expected value of a sample mean would probably just look like the sample mean that we have, okay? If instead of knowing about the average height over here of all students within the high school, we just know about our sample of 50 students and their average height within the school, the best guess that we have is that other samples will behave similarly, okay? So when you have given to you only sample information, you estimate the mean, okay? And similarly, instead of calling it the standard deviation, if you don't have sigma, you call it the standard error. And we estimate that as, instead of sigma over rad n, that is S over rad n, okay? So in blue, you have another estimate. Well, notice, to estimate a normal bell curve, if we think that's the right tool, which I'll show you here in a bit that it isn't, but if we think it's the right tool, that requires two things. It requires a sample mean and a sample standard deviation. Well, naturally, sampling variability says those things can vary from sample to sample. Of your 50 students, you may see one sample mean of 5'4", the next sample mean of 5'7". So that means that the accuracy of whatever bell curve you draw is going to be thrown off a little bit for your sample mean. And it also means that based upon the fact that to estimate your standard deviation, you're using a sample standard deviation, that too can throw off the accuracy of your bell curve. All right? So you have two things coming from your sample to estimate mean and standard deviation. Well, let's contrast here real quick. So let's say we don't have the population proportion and we want to describe sample proportions. So let's say that we are given p hat, okay? And that's the best we can do. Well, we would expect that if we don't know the whole population proportion, maybe extend that discussion of milk, maybe we want p to be the population proportion of everyone within the United States who is drinking milk. Good question for dairy farmers. Something that's really hard to pinpoint, but we can take samples and know from our samples sample proportions of people who drink milk. Okay, so the best guess we have for how another sample proportion would behave would be just like the sample proportion that we have to begin with. All right, that's our estimate. That blue arrow indicates we're estimating the expected value of p hat with our sample. Okay, and the standard error of p hat would just be, instead of rad pq over n, it's short on space here, p hat, q hat, all over n within the radical. Okay, and that's our estimate of the standard deviation. All right, well, this is what I want you to pick up on, is that to estimate the mean and the standard error for sample means, you're using two different things from the sample. But to estimate the mean and standard error for proportions, you actually just need the same thing 2 times. The sample proportion appears both times in your mean and in your standard deviation. So when you use sample data to estimate sampling distributions of proportions, you have less sampling variability that will be a problem for you, because you're just using a single statistic to make your best guess at mean and standard deviation, whereas you're using 2 statistics for the sample means. So if you look back with me real quick, when we talked about sample proportions, we built the following. Let's just write things we looked at. Okay, we saw, first of all, we saw a sampling distribution, which we've kind of built just above what we're writing now. We saw a confidence interval for p hat. We saw a hypothesis test. For p hat. We saw all 3 of those things, but on the other side of the spectrum, when we were looking at sample means, let's just write saw. Things we saw for sample means, we actually just saw a sampling distribution of a sample mean, because a confidence interval and a hypothesis test depend upon sample data. And when you don't have population information, you just have sample data, the bell curve actually breaks down. All right, so let me write for you real quick we're going to introduce the confidence interval for one mean by just showing how it's similar to the confidence interval for one proportion. The confidence interval for one proportion is centered on p hat. Okay? Your sample information is in the middle of your confidence interval. Then you go some number of standard deviations to the left and to the right to capture your percent confidence interval, and your standard error is used instead of a standard deviation because it's coming from sample data, not from population data. Okay, so if you had a 68% confidence interval, you would be one standard error to the left and to the right of your sample data. Okay, well, confidence interval for one mean. And before I go to this, obviously this was all built off the normal bell curve. We drew many of those in chapters 18 through 22. Okay, so a confidence interval for one mean, similarly, is centered on your sample data, x bar. And because when you use sample information to try and talk about a confidence interval or a hypothesis test for sample means, again, that uses two statistics. That makes the accuracy of the normal bell curve break down a little bit. We actually use the t-distribution. And I mean, as you can see here, all that I did is I took a normal bell curve from the left to the right, I shrunk it down, stretched it out, and that gives you the essential shape of the t-distribution. It is flatter, it doesn't have so prominent a central peak, and it's got hips. It's got more of the distribution in the bottom and top tails or the wings of the normal bell curve. Okay, it's a less accurate distribution. Okay, so instead of a z-score, you use a t-score. That's just the number of standard errors you go to the left and to the right of your sample information. Okay, so if you want it doesn't quite come out to be this way, but essentially, if you want a 68% confidence interval for a sample mean, there too you're just going, instead of one z-score left and right, you're essentially going one t-score left and right. Okay. Oh, and forgot to fill in the standard error, which we've already filled in. Rad p hat, q hat, all over n versus the S over rad n, sample standard deviation over rad n. Okay, so we're starting to talk about this t-distribution. Let me show you a little bit more of the details as to how it compares to the normal bell curve. There are technically an infinite number of t-distributions, which don't freak out about that. That doesn't mean that there's anything you have to memorize with regard to all those different t-distributions, aside from the fact that you need to know that every t-distribution, let's look at the one here that's in the boldest of all of them, with degrees of freedom 4. Okay, this guy, it too, just like a normal bell curve, it is centered on your whatever mean you have. But well, if we're talking about sample means, it would be centered on the expected value of x bar is just x bar. Okay, that's your mean. Standard error to the left and to the right is just the S over radical n that we've been talking about for a few slides now. Okay, S over radical n. I'm going to put negative S over radical n because you'd subtract your standard error to get over there to the left. But it keeps track of two. Each of the t-distributions keeps track of degrees of freedom. The degrees of freedom, you can kind of see by this picture, it is, well, first of all, let's start by taking a look at the equation. From the equation, you can tell it's related to your sample size. You take your sample size, if you've got 50 students that you're looking at with respect to their heights at Yorktown High School, you subtract off 1, so the t-distribution you would use would have degrees of freedom of 49. Okay? The higher the degrees of freedom, as you can see in this picture, the more prominent the central peak, the less the t-distribution has those hips, has more of the distribution in the tails like we've been talking about. Okay? And actually, as your sample size goes to infinity, the t-distribution becomes the normal bell curve. Okay? Now, I'll be honest with you. Landon Zachary had some great questions about, okay, Mr. Shelton, where does this come from? This feels like we're just pulling another normal bell curve out of our butts here. Well, honestly, I cannot explain to you the mathematics behind where all of this comes from. I know I've not encountered it at the bachelor's level with an undergraduate degree. I know that some of this requires what's called moment generating functions to actually explain where these bell curves come from, and that stuff is graduate level mathematics. So it's tough. We can work with the t-distribution, but I can't give you a mathematical derivation of it. All right. So when you use the t-distribution, you've got thankfully not a whole lot of conditions. In the first two, you've used a lot. You're going to use randomization. You're going to use 10%. And in general, if you're asking yourself, hey, should I use what condition should I check? If you're going to err on the side of caution, check the randomization condition and the 10% condition for every test or confidence interval if you're not sure, if you've forgotten what was on those, the summary sheet from 18 through 22 that I gave you guys. The last condition is unique to sample means. It's the nearly normal condition. And basically, you're looking at your sample data, and you're going to say, okay, is the sample size small? Is it less than 15? If so, we want a histogram of our sample data to be unimodal and symmetric. That means make sure that it looks a lot like a bell curve. Okay, central peak, and to either side of the central peak, it takes on basically the same shape. Next up, you're going to look at sample sizes between 15 and 41. That's 16 through 40, really. And here, we care a lot about making sure that it's unimodal. It has one central peak, but we don't care so much as to whether or not it's symmetric. Okay, at that sample size, we can fudge a little bit. And then at greater than 40, we are going to fudge with unimodality, and we'll fudge with symmetry. We still build the histogram to check the condition, and we'll draw a sketch of it quickly. It's not something that needs to be super accurate. We'll draw a sketch of it, and that'll check the condition. And I'll show you how to do that next. Okay, so lots of theory, I guess. We're just introduction of new. I don't know how theoretical it is. Let's go ahead and jump into this problem regarding Trip Hammer Road. Okay, so Trip Hammer Road is a busy street that passes through a residential neighborhood. Residents there are concerned that vehicles traveling on Trip Hammer often exceed the speed limit of 30 miles an hour. The local police sometimes places a radar speed detector by the side of the road, and as a vehicle approaches, this detector displays the vehicle's speed to its driver. The police hope that drivers will slow down if they are reminded of their speed. We want to build a 90% confidence interval for the mean speed of all vehicles traveling on Trip Hammer from the data collected below. Okay, so notice, yeah, we're building a confidence interval, but you have numerical data that you're working with. Whenever you would build a 90% confidence interval for a proportion by contrast, you would not be told, for instance, as you see here, the speeds of cars as they're driving along the Trip Hammer. For proportions, you're working with qualitative data. If you wanted to build a 90% confidence interval for proportions and you had all the data in front of you like you do here, you might see, oh, okay, voted for Romney, voted for Obama, or drinks milk, doesn't drink milk. Okay, proportions focus on qualitative data. The means are always quantitative. Okay, so let's go ahead and, because we're building a confidence interval, we don't have any hypotheses to worry about. We'll do something like that next slide. Let's go ahead and show the conditions here real quick. All right, so we have randomization. We're not told that the data is random, so we'll assume it's representative. All right, 10% condition. So the population we're comparing these 23 data values to, that's all the speeds that you see here, is going to be, well, we're worried about car speeds along Trip Hammer, so we're going to assume that 23 cars, or car speeds, I guess to be most accurate, car speeds is less than 10% of all car speeds along Trip Hammer. On Trip Hammer, okay? So there's the 10% condition. And then lastly, you have the nearly normal condition, which we're going to check real quick. I'll bust out Wabbit. This is where you guys, if you've got a calculator, make sure you practice this. It's been a little while since we built a lot of histograms. I'll pull up Wabbit mu, excuse me. And let's see what we get. Hit the OK button here. I believe I've already entered in the data. I had done that for Friday's class. Oh boy, such a fast computer. Oh, there we go. Stat, edit, and in the first list, I've got, 23 data values. I'm going to assume that they're the same as what I needed. Okay, so once you've got your data into L1 or L2 or whatever, you're going to go to stat plot. Make sure that you've got one plot on. If for some reason it's going to give you an error once you zoom stat, check too that you don't have any graphs on at the y equals menu. I've seen this a lot where someone has like a, I don't know, something from calculus or pre-calculus that's set up here. In addition to a stat plot, it won't graph both at the same time. Alright, so plot 1 is on, chosen a histogram. The X list is the data list, and we will go to quit, zoom stat, and there you go. Okay, so we're going to consider, well, the nearly normal condition says we will meet the condition so long as the data takes on a normal bell curve like shape based upon the sample size. Well, if we've got 23 data values here, which we added up before, we don't have to have a symmetric distribution, but we do need a unimodal distribution. So we are going to draw what we see. Okay, so I saw essentially, okay, here we go. So essentially something like this. Third peak was the biggest. The next two were a reasonable size. I saw a sixth peak that was lower, and then the seventh peak was low. Okay, something like that. And I would say that the condition is met because the distribution of data is unimodal. Okay, so there are your conditions. All right, let's go ahead and do the mechanics next. Again, no hypotheses to worry about with this confidence interval. So instead of a normal bell curve, we're using a t-distribution, which you can draw it identically to a bell curve if you want. And my degrees of freedom I'll post beside every t-distribution, partly because that tells me, oh, I'm working with the t-distribution. When I get to my calculator functions, I want to use the t functions, not the normal bell curve functions. Well, your degrees of freedom is 1 less than your sample size, so that's 22 here. We need the expected value of the sample means along this street. Well, what you can do, we know that that should be equal to the sample mean of our data. You can get that very easily because you've entered your data into a list. You can go stat, calc, 1var stats, make sure that the list that you've entered your data into is your list here, frequency list you don't worry about, calculate that. And there you go. X bar is 31.04. 31.04. Your standard error of X bar is equal to, that's your sample standard deviation, so it's 4.25 here, over the square root of your sample size, square root of 23 equals, let's see, what did I find? Well, I think that was, going from memory here, I might be wrong about this. For some reason I didn't write this in my notes. Oh yeah, it is 0.89. Okay, cool. All right, so here's our confidence interval centered on 3104. 0.89 to either side takes us to 31.93 and 30. Just to make sure that I'm doing this correctly, 31.04 minus your 0.89, and there we go, 30.15. Okay. So we wanted a 90% confidence interval. So that's going to be past our standard error in either direction. Okay, so here's your 90%. Your 90% confidence interval is the following. It's your x bar plus or minus your t-score for 22 degrees of freedom times your standard error, which we've also found. So this is your 31.04 plus minus, as to how to get the t-score here, well, just like you would any other time, the t-score is the number of standard errors you move to the right or to the left. I tend to focus on the higher of the two, okay, which is equal to, instead of inverse norm, you do inverse t with regard to the percent of the whole distribution less than that point. Well, there's 90% in the middle, 5% on the left wing, so it's 0.95. And your degrees of freedom you're going to enter as well. Let me show you on the calculator where this is. This is second distribution inverse t with 0.9522. As you can see, I've used that on Friday, and calculator says, I think it's 1.717. Yeah, there we go. 1.717. This we've calculated to be 0.89. The whole confidence interval goes from 29.52 to 32.56. Okay? So with 90% confidence, we think, notice that 30 miles an hour is in your confidence interval. With 90% confidence, we believe that it's possible people driving along Trip Hammer Road are going the speed limit, even though your sample mean is a little high. It's still possible. Okay. Second example we're going to do here together. We've looked at a confidence interval. Now let's build a hypothesis test for sample means. We're not going to go through the conditions because they're identical to what we just did last slide. Same data we're going to use. So let's start with your hypotheses. Just as with any other null hypothesis, the null is never an inequality. It's always a particular value. We want to know if people are driving 30 or if they're going over 30. Okay? So mu, the population mean we care to pin down, we're going to assume is 30, that people are obeying the law. Okay, there's your innocence assumption. And then the alternative will be that the population mean of cars driving along Trip Hammer is greater than 30. Okay, so your mechanics next. Set up similar to last slide. Okay, we're going to the expected value. Let's see, degrees of freedom we'll set over here 22 because this is a t distribution. The expected value, the sample mean we said from last slide was 31.04. Standard error of a sample mean was 0.089. Wait, or 0.89. 0.89. 0.89. Okay. So we'll set up basically the same bell curve. 31.04 in the middle, 31.93, and 30.15. Okay, so what do we do next? Well, oh wait, I'm being a dummy. This isn't right. This isn't right. We don't use all that. Okay? We are going to, we'll use a t distribution, but I'm not moving from the null hypothesis, am I? Okay, degrees of freedom, it equals 22. The expected value of a sample of cars driving along Trip Hammer should just be what your null hypothesis assumes. 30. It's not the same as the confidence interval. You're going to set it up to be 30. Your standard error is equal to the same thing that we used last slide, because notice the null hypothesis here doesn't make any claim about what the standard deviation is. So you have to work from your sample standard deviation over that square root of 23, your sample size, like we've done before. So you get the same standard error, 0.89. So you're 30.89, excuse me for that, and 29.11. Now you fit your sample mean of 31.04 on the distribution. You ask yourself, okay, what's the probability that your sample mean be that far away from 30? Is the alternative true? Okay, so we're going to find this area under the curve. To do that, same types of procedures you would do for a normal bell curve. You're going to say, well, let's find, instead of a z-score, a t-score for these 22 degrees of freedom. You take your sample data, you subtract off your mean, you divide through by your standard error. This comes out to be 1.17. And now, instead of normal CDF, you use TCDF. And this will get you the p-value. So your p-val is equal to TCDF from 1.17 up to like a